There are 5 chapters in Chemistry 2: Structures and Bonding, Structure and Properties, How much, Rates and Energy, and Salts and Electrolysis. Elements react together to form compounds by gaining or losing electrons, or by sharing electrons. The elements in Group 1 react with the elements in Group 7. As they react, atoms of Group 1 elements can each lose 1 electron to gain the stable electronic structure of a noble gas. This electron can be given to an atom from Group 7, which then also achieves the stable electronic structure of a noble gas. Ionic compounds are held together by strong forces of attraction between the oppositely charged ions. This is called ionic bonding. Besides the elements in groups 1 and 7, other elements that can form ionic compounds include those from groups 2 and 6. For example, magnesium and oxygen to form magnesium oxide. Calcium reacts with chlorine to form calcium chloride, another ionic compound. The charges on the ions in an ionic compound always cancel each other out. The formula of an ionic compound shows the ratio of ions present in the compound. Sometimes we need brackets to show the ratio of ions in a compound. For example, magnesium hydroxide, which is written Mg in brackets OH twice. When naming compounds, we use the ending IDE, ide, for simple non-metal ions such as oxide or sulfide. However, we use ate, ATE, for ions that include oxygen, such as sulfate, nitrate, and carbonate. You don't have to learn the charges on ions, they're on the datasheet. Think of each symbol as a single atom and the formula of each ion as a single ion. Small numbers multiply only the symbol they follow. Brackets are needed when there is more than one type of atom in the ion being multiplied. Covalent bonds are formed when atoms share a pair of electrons. Many substances containing covalent bonds consist of simple molecules, for example hydrogen chloride, water, and methane. But some have giant covalent structures. The best example of this is diamond. The atoms in metals are closely packed together and arranged in regular layers. We can think of metallic bonding as positively charged metal ions which are held together by electrons from the outermost shell of each metal atom. These delocalized electrons are free to move throughout the giant metallic lattice. It takes a lot of energy to break the many strong ionic bonds which hold a giant ionic lattice together, so ionic compounds have high melting points. They are all solids at room temperature. Ionic compounds will conduct electricity when we melt them or dissolve them in water. That's because their ions can then move freely around and can carry charge through the liquid. Remember that every ionic compound has a giant structure. The oppositely charged ions in these structures are held together by strong electrostatic forces of attraction. These act in all directions. Substances made up of simple molecules have low melting points and boiling points. The forces between simple molecules are weak. These weak intermolecular forces explain why substances made of simple molecules have low melting points and boiling points. Simple molecules have no overall charge, so they cannot carry electrical charge. Therefore, substances made of simple molecules do not conduct electricity. Remember, although the covalent bonds in molecules are strong, the forces between molecules are weak. Some covalently bonded substances have giant structures. These substances have high melting points and boiling points. Graphite contains giant layers of covalently bonded carbon atoms. However, there are no covalent bonds between the layers. This means they can slide over each other, making graphite soft and slippery. The atoms in diamond have a different structure and cannot slide like this, so diamond is a very hard substance. Graphite can conduct electricity because of the delocalized electrons along its layers. As well as diamond and graphite, carbon also exists as fullerenes, which can form large cage-like structures based on hexagonal rings of carbon atoms. Remember, giant covalent structures are held together by covalent bonds throughout the lattice. We can bend and shape metals because the layers of atoms or ions in a giant metallic structure can slide over each other. Delocalized electrons in metals enable electricity and heat to pass through the metal easily. If a shaped memory alloy is deformed, it can return to its original shape on heating. Monomers affect the properties of the polymers that they produce. Changing reaction conditions can also change the properties of the polymer that is produced. Thermo Softening polymers will soften or melt easily when heated. Thermo Setting polymers will not soften but will eventually char if heated very strongly. Electrical sockets are made out of Thermo Setting plastics. If the plug or wires get hot, the socket will not soften. Nanoscience is the study of small particles that are between 1 and 100 nanometers in size. Nanoparticles behave differently from the materials they are made from on a large scale. New developments in nanoscience are very exciting, but will need more research into possible issues that might arise from their increased use. The relative mass of protons and neutrons is 1. The atomic number of an atom is its number of protons, which equals its number of electrons. The mass number of an atom is the total number of protons and neutrons in its nucleus. Isotopes are atoms of the same element with different numbers of neutrons. We compare the masses of atoms by measuring them relative to atoms of carbon-12. We work out the relative formula mass of a compound by adding up the relative atomic masses of the elements in it in the ratio shown by its formula. One mole of any substance is its relative formula mass in grams. You don't have to remember the relative atomic masses of elements, but practice calculating the mass of 1 mole of different substances from their formula and the relative atomic masses that you are given. The relative atomic masses of the elements in a compound and its formula can be used to work out its percentage composition. We'll take magnesium oxide as an example. So what percentage of the mass of magnesium oxide is actually magnesium? Well, first we need to know the formula of magnesium oxide. This is MgO. The relative atomic mass of magnesium is 24, and the relative atomic mass of oxygen is 16. Adding these together gives us the relative formula mass of magnesium oxide. 24 plus 16 is 40. So, in 40 grams of magnesium oxide, 24 grams is actually magnesium. The fraction of magnesium in the magnesium oxide is the mass of magnesium divided by the total mass of the compound, magnesium oxide. This is 24 divided by 40. So the percentage of magnesium in the compound is 24 divided by 40 multiplied by 100, which gives you 60%. We can calculate empirical formulae given the masses or percentage composition of elements present. Balanced symbol equations tell us the number of moles of substances involved in a chemical reaction. We can use balanced symbol equations to calculate the masses of reactants and products in a chemical reaction. The yield of a chemical reaction describes how much product is made. The percentage yield of a chemical reaction tells us how much product is made compared with the maximum amount that could be made, i.e. 100%. Factors affecting the yield of a chemical reaction include product being left behind in the apparatus and difficulty separating the products from the reaction mixture. It is important to maximise yield and minimise energy wasted to conserve the Earth's limited resources and reduce pollution. In all the reactions we've looked at so far, the reactants react and form products. We show this by using an arrow pointing from the reactants to the products. But in some reactions, the products can react together to make the original reactants again. We call this a reversible reaction. A reversible reaction can go in both directions, so we use two arrows in the equation. One arrow points in the forwards direction and one backwards. Ammonium chloride breaks down on heating. It forms ammonia gas and hydrogen chloride gas. This is an example of thermal decomposition. The two gases rise up the test tube. When they cool down near the mouth of the tube, they react with each other. The gases reform ammonium chloride again. The white solid forms on the inside of the glass. Additives may be added to food in order to improve its appearance, taste, and how long it will keep, i.e. its shelf life. Food scientists can analyse foods to identify additives, for example by using paper chromatography. Modern instrumental techniques provide fast, accurate and sensitive ways of analysing chemical substances. Although simpler to use than bench chemistry methods, instrumental methods still need trained technicians to operate them. Compounds in a mixture can be separated using gas chromatography. Once separated, compounds can be identified using a mass spectrometer. The mass spectrometer can be used to find the relative molecular mass of a compound from its molecular ion peak. We can find out the rate of a chemical reaction by following the amount of reactants used up over time. Alternatively, we can find out the rate of reaction by following the amount of products made over time. The slope of the line at any given time on the graphs drawn from such experiments tell us the rate of reaction at that time. The steeper the slope, the faster the reaction. Particles must collide with a certain amount of energy before they can react. The minimum amount of energy that particles must have in order to react is called the activation energy. The rate of the chemical reaction increases if the surface area of any solid reactant is increased. This increases the frequency of collisions between reacting particles. Remember, particles collide all the time, but only some collisions lead to reactions. Increasing the number of collisions in a certain time and the energy of collisions produces faster rates. Larger surface area does not result in collisions with more energy, but does increase the frequency of collisions. Reactions happen more quickly as the temperature increases. Increasing the temperature increases the rate of reaction because particles collide more frequently and more energetically. More of the collisions result in a reaction because a higher proportion of particles have energy greater than the activation energy. Increasing the concentration of reactants in solutions increases the frequency of collisions between particles and so increases the rate of reaction. Increasing the pressure of reacting gases also increases the frequency of collisions and so increases the rate of reaction. Remember, increasing concentration or pressure does not increase the energy with which the particles collide. However, it does increase the frequency of collisions. A catalyst speeds up the rate of a chemical reaction. A catalyst is not used up during a chemical reaction. Different catalysts are needed for different reactions. Remember, catalysts change only the rate of reactions. They do not change the products. The transition metals platinum and palladium are used in the catalytic converters in cars. Catalysts are used whenever possible in industry to increase rate of reaction and reduce energy costs. Traditional catalysts are often transition metals or their compounds, which can be toxic and harm the environment if they escape. Modern catalysts are being developed in industry which result in less waste and are safer for the environment. Energy may be transferred to or from the reacting substances in a chemical reaction. A reaction in which energy is transferred from the reacting substances to their surroundings is called an exothermic reaction. A reaction in which energy is transferred to the reacting substances from their surroundings is called an endothermic reaction. Remember that exothermic reactions involve energy exiting or leaving the reacting chemicals, so the surroundings get hotter. In endothermic reactions, energy moves into the reacting chemicals, so the surroundings get colder. In reversible reactions, one reaction is exothermic and the other is endothermic. In any reversible reaction, the amount of energy released when the reaction goes in one direction is exactly equal to the energy absorbed when the reaction goes in the opposite direction. Exothermic changes can be used in hand warmers and self-heating cans. Crystallization of a supersaturated solution is used in reusable warmers. However, disposable one-off warmers can give off heat for longer. Endothermic changes can be used in instant cold packs for sports injuries. Acids are substances which produce hydrogen ions when we add them to water. Bases are substances that will neutralize acids. An alkali is a soluble hydroxide. Alkalis produce hydroxide ions when we add them to water. We can use the pH scale to show how acidic or alkaline a solution is. When we react an acid with a base, a neutralization reaction occurs. The reaction between an acid and a base produces a salt and water. Salts can also be made by reacting a suitable metal with an acid. This reaction produces hydrogen gas as well as a salt. A sample of the salt made can then be crystallized out of solution by evaporating off water. An indicator is needed when a soluble salt is prepared by reacting an alkali with an acid. Insoluble salts can be made by reacting two solutions to produce a precipitate. Precipitation is an important way of removing some metal ions from industrial wastewater. Electrolysis breaks down a substance using electricity. Ionic compounds can only be electrolyzed when they are molten or in solution. That's because their ions are then free to move to the electrodes. In electrolysis, positive ions move to the negative electrode, while negative ions move to the positive electrode. In electrolysis, the ions move towards the oppositely charged electrodes. At the electrodes, negative ions are oxidized, while positive ions are reduced. When electrolysis happens in water, the less reactive element between hydrogen and the metal is usually produced at the negative electrode. At the positive electrode, we often get oxygen gas
given off from discharged hydroxide ions. Remember, oxidation and reduction reactions don't have to involve oxygen. More generally, they involve the transfer of electrons. Remember oil rig. Oxidation is loss, reduction is gain of electrons. Aluminium oxide is electrolyzed in the manufacture of aluminium metal. The aluminium oxide is mixed with molten cryolite to lower its melting point. Aluminium forms at the negative electrode and oxygen at the positive electrode. The positive carbon electrodes are replaced regularly as they gradually burn away. When we electrolyze brine, we get three products: chlorine gas, hydrogen gas, and sodium hydroxide solution, which is an alkali. Chlorine is used to make bleach, which kills bacteria and is used to make plastics. Hydrogen is used to make margarine. Sodium hydroxide is used to make bleach, paper, and soap. We can electroplate objects to improve their appearance, protect their surface, and to use smaller amounts of precious metals. The object to be electroplated is made the negative electrode in an electrolysis cell. The plating metal is made the positive electrode. The electrolyte contains ions of the plating metal.